Hello there, and welcome to the Sleepy Science Society. Tonight, we're drifting back through an unimaginable expanse of time to witness one of the most dramatic transformations in the history of life on Earth. A moment when the world changed forever in ways both sudden and lingering. A moment that ended the age of giants and opened the door to nearly everything that followed, including us. Before we begin this quiet journey into deep time, I want to invite you to join our growing community of sleepy thinkers. If you find peace in these gentle explorations of science, a like or subscription helps other wandering minds discover this corner of calm. It's a small gesture that makes a real difference, one restful soul at a time. But there's no hurry. For now, all you need to do is settle in. Let your breathing slow. Allow your muscles to release their tension. Feel the weight of your body sinking softly into wherever you're resting. We're going to move through time tonight backwards, through millions upon millions of years, to a world that would seem alien to us now. A world of giants. A world of creatures so magnificent, so perfectly adapted to their environment, that their reign seemed eternal. And yet, in geological terms, it ended in the blink of an eye. The story we're exploring tonight is the story of dinosaur extinction. It's a mystery that puzzled scientists for over a century. A puzzle with missing pieces scattered across continents and buried beneath oceans. It's a tale of cosmic violence meeting a thriving planet, of fire and ice, darkness and devastation. It's also a story of resilience, of survival against impossible odds, and of new beginnings rising from catastrophic endings. As you rest, imagine standing on an Earth from 66 million years ago. The air is different. The plants are unfamiliar. The sounds that echo through forests and across plains belong to creatures that no living human has ever heard. This is the world we're about to explore, the world that was about to change in ways its inhabitants could never have imagined. Let yourself drift into this ancient time as we begin to unravel what happened when the age of dinosaurs came to its sudden, violent end. The world before. To understand what was lost, we must first understand what existed. 66 million years ago, Earth was a radically different place from the world we know today. This was the late Cretaceous period, the final chapter in the age of dinosaurs, and life had reached a peak of diversity and complexity that would not be seen again for millions of years. The continents were still moving, drifting slowly across the planet's surface as they had been for billions of years. North and South America were separated by a vast seaway. India was an island continent, slowly making its journey northward toward its eventual collision with Asia. The Atlantic Ocean was younger and narrower. Ancient seas covered large portions of what we now think of as dry land, creating warm, shallow marine environments that teemed with life. The climate was dramatically warmer than today's world. There were no polar ice caps. Even the regions near the North and South Poles experienced temperate conditions, with forests growing where today we find only ice and snow. Ocean temperatures were warm from pole to equator, creating a world where tropical and subtropical conditions extended far beyond their current boundaries. Rainforests flourished across vast areas. Palm trees grew in what is now Alaska. Crocodiles basked on riverbanks in the Arctic regions. This warm, wet world was paradise for reptiles. Dinosaurs had dominated terrestrial ecosystems for over 160 million years by this point. They had diversified into an astonishing array of forms, occupying nearly every conceivable ecological niche on land. In the forests of North America, massive sauropods like Alamosaurus still roamed, though these long-necked giants were less common than they had been in earlier periods. Herds of hadrosaurs, the duck-billed dinosaurs, migrated across vast plains, their elaborate head crests used for communication and display. Predators stalked these herbivores with sophisticated hunting strategies. Tyrannosaurus rex, perhaps the most famous dinosaur of all, ruled the late Cretaceous ecosystems of western North America. These massive predators stood over 12 feet tall at the hip and stretched more than 40 feet from nose to tail. Their skulls alone measured over 5 feet long, packed with teeth the size of bananas, but T-Rex was not alone. Other tyrannosaurs hunted across Asia. In South America, enormous predators like Giganotosaurus had evolved independently, showing that the formula for apex predation had been solved multiple times. The skies belonged to pterosaurs, the flying reptiles that had taken to the air long before birds evolved. By the late Cretaceous, these creatures had reached remarkable sizes. Quetzalcoatlus, one of the largest. Pterosaurs had a wingspan that stretched over 30 feet, making it larger than many small aircraft. These giants soared over ancient seas and continents, using thermal currents to stay aloft with minimal effort. Birds had also evolved by this time, though they were still relatively small and had not yet diversified into the thousands of species we know today. These early birds shared the skies with their pterosaur cousins, exploiting different ecological niches. Some were beginning to develop the characteristics that would later help them survive the coming catastrophe. The oceans were equally alive with reptilian giants. Mosasaurs, massive marine lizards that could grow over 50 feet long, were apex predators of the seas. They hunted everything from fish to other marine reptiles, their powerful jaws lined with teeth designed for gripping and tearing. Plesiosaurs, with their long necks and paddle-like limbs, swam through ancient waters. Sea turtles, some growing to enormous sizes, navigated the warm currents. Beneath these giants, the ocean floor and shallow seas supported an incredible diversity of invertebrate life. Ammonites, spiral-shelled relatives of modern squid and octopi, existed in thousands of species. Some were tiny, no larger than a coin. Others grew to several feet in diameter. Their beautiful, mathematically precise shells are among the most commonly found fossils from this era, frozen moments of ancient ocean life. Mammals existed during this time, but they were small, mostly nocturnal creatures living in the shadows of the dinosaurs. They had been around for nearly as long as dinosaurs themselves. but they had never managed to break free from the constraints that kept them small and ecologically marginal. They occupied niches as insect eaters, seed eaters, and small predators. Some had even begun to develop more specialized lifestyles, with early forms of gliding mammals and semi-aquatic species appearing in the fossil record. The plant life of the late Cretaceous was a mixture of ancient lineages and newer innovations. Flowering plants, angiosperms, had appeared relatively recently in geological terms, but they were diversifying rapidly. Forests that had once been dominated by conifers and ferns now included deciduous trees. The first grasses were beginning to appear, though they had not yet spread to dominate vast prairies as they would in later ages. Magnolias bloomed in ancient forests. Water lilies floated on the ponds and slow-moving rivers. This was a world of incredible biological richness, a planet where life had evolved, adapted, and flourished for hundreds of millions of years. Ecosystems were complex, interconnected webs of relationships between predators and prey, plants and herbivores, decomposers, and nutrient cycles. Energy from the sun powered photosynthesis in plants, which fed herbivores, which fed carnivores, in chains that extended from the smallest insects to the largest dinosaurs. And yet, for all its apparent stability, for all the millions of years these ecosystems had persisted and evolved, the entire system was far more fragile than it appeared. Life on Earth had recovered from mass extinctions before. The planet had witnessed catastrophic events that wiped out large percentages of species. But the organisms alive in the late Cretaceous had no knowledge of this history, no sense of the vulnerability inherent in existence on a small planet in a vast cosmos. They simply lived, as life does, moment to moment, generation to generation, under skies that had been stable and predictable for millions of years. The great herds migrated with the seasons. Predators hunted according to strategies honed over countless generations. Plants bloomed and spread their seeds. Life continued its ancient patterns, unaware that those patterns were about to be shattered daime in the most violent way imaginable. The discovery of the iridium layer. For most of human history, the existence of dinosaurs was unknown. It wasn't until the early 19th century that scientists began to realize that the strange bones emerging from rocks were the remains of extinct animals, unlike anything alive today. As more fossils were found and studied, a picture emerged of a lost world populated by giants. But for over a century, the question of why these creatures vanished remained one of science's most enduring mysteries. By the mid-20th century, paleontologists had established that dinosaurs disappeared at what's called the Cretaceous-Paleogene boundary, originally known as the Cretaceous Tertiary boundary or KT boundary. This was a distinct layer in the geological record, visible in rocks around the world, that marked a dramatic shift in the types of fossils found. Below this boundary, dinosaur fossils were abundant. Above it, they vanished completely, except for the lineage that had evolved into birds. Theories about their extinction ranged widely. Some suggested gradual climate change. Others proposed disease pandemics spreading through dinosaur populations. Some thought competition from newly evolving mammals might have played a role. There were ideas about changing plant communities, shifting sea levels, or long-term volcanic activity slowly poisoning the environment. Each theory had its supporters, but none could fully explain the pattern seen in the rocks. A world full of dinosaurs, then a boundary layer, then a world without them. The breakthrough came in the late 1970s in an unlikely place. In the medieval town of Gubbio, nestled in the hills of central Italy, there's a narrow gorge where limestone cliffs reveal millions of years of Earth's history in layered stone. These rocks formed at the bottom of an ancient ocean, slowly accumulating sediment year after year, century after century, building up a record of the past in compressed layers. Walter Alvarez, a geologist working at the University of California, Berkeley, was studying these rocks, particularly interest in understanding the rate at which sediment had accumulated. He noticed a thin layer of clay right at the KT boundary, sandwiched between limestone layers. This clay layer appeared in many other locations around the world, always at exactly the same point in geological time, always marking the boundary between the age of dinosaurs and the age that followed. Walter asked his father, Luis Alvarez, to help investigate this mysterious clay layer. Luis was a physicist, a Nobel Prize winner, whose work had ranged from radar systems to particle accelerators. Together with the nuclear chemists Frank Asaro and Helen Mitchell, they decided to analyze the chemical composition of the clay layer, hoping it might reveal how long it had taken to form. What they found was completely unexpected. The clay layer contained high concentrations of iridium, an element that's extremely rare in Earth's crust. Iridium is a dense, silvery white metal belonging to the platinum group. On Earth's surface, it's found in tiny quantities, typically measured in parts per trillion. But the Gubbio clay layer contained iridium in concentrations 30 times higher than the rocks above and below it. This discovery was puzzling until they considered where iridium is more common. In space, in asteroids and meteorites, iridium exists in much higher concentrations. These objects formed from the primordial material of the solar system, material that includes higher proportions of heavy elements that sank to Earth's core billions of years ago when our planet was still molten. The surface of the Earth was largely depleted of iridium, but objects from space still contained it in abundance. The Alvarez team proposed a revolutionary hypothesis. What if the iridium layer represented the fallout from a massive asteroid impact? An object perhaps 6 miles in diameter, traveling at tens of thousands of miles per hour, slamming into Earth with unimaginable force. Such an impact would vaporize the asteroid, sending its material, including iridium, into the atmosphere. This material would encircle the globe, eventually settling back to Earth as a thin layer covering the entire planet. The hypothesis was elegant and explained several mysteries at once. It explained the worldwide distribution of the iridium-rich clay layer. It explained the suddenness of the extinctions. And it provided a mechanism catastrophic enough to have caused such widespread destruction. The energy released by such an impact would be equivalent to billions of nuclear weapons detonating simultaneously. The immediate effects would be devastating. The long-term effects would alter the climate of the entire planet. When the Alvarez team published their findings in 1980, the scientific community reacted with a mixture of fascination and skepticism. The idea seemed almost too dramatic, too much like science fiction. Catastrophism, the notion that sudden violent events shape Earth and history, had fallen out of favor in geology. The prevailing view was uniformitarianism, the principle that geological processes occurring today have operated throughout Earth's history at roughly the same rates. Gradual change, not catastrophe, was supposed to be the norm. But the evidence was compelling. Other researchers began looking for the iridium layer at different locations around the world. They found it in Denmark. They found it in New Mexico. They found it in Spain, in New Zealand, in dozens of sites on every continent. Always the same pattern. A thin layer enriched in iridium, always at the same moment in geological time, always at the boundary between the Cretaceous and Paleogene periods. The iridium wasn't the only unusual feature of this boundary layer. Researchers found shocked quartz, mineral grains that had been subjected to pressure so extreme they could only be explained by an asteroid impact or a nuclear explosion. They found tiny glass spherules called microtectites, formed when rock is melted and ejected into the atmosphere, cooling into droplets during its ballistic trajectory. They found soot and charcoal, evidence of massive wildfires. All of these discoveries pointed to the same conclusion. Something catastrophic had happened 6 million years ago. Yet one crucial piece of evidence was missing. If an asteroid had hit Earth, where was the crater? An object large enough to cause a global extinction should have left behind a massive scar on the planet's surface. The search for this crater became one of the most important scientific quests of the 1980s. Researchers calculated that the crater should be somewhere between 100 and 200 miles wide. It should be approximately 6 million years old. And it should be buried somewhere on Earth's surface, perhaps hidden beneath sediment or beneath the ocean, waiting to be found. The hunt was on. Scientists began looking at known impact structures, checking their ages. They examined satellite imagery for circular features that might be buried craters. They analyzed magnetic and gravity data, looking for anomalies that could indicate a large impact structure. For years, the search came up empty. Some scientists began to wonder if perhaps the crater was in the ocean, where it might be harder to detect, or whether it had been destroyed by geological processes over the millions of years since the impact. But others continued searching, convinced that the evidence was too strong for the asteroid hypothesis to be wrong. The crater had to exist. It had to be somewhere. And eventually, through a combination of persistence, luck, and careful detective work, it was found. Finding Chicxulub. The discovery of the Chicxulub crater is a story of serendipity, persistence, and connections made across decades and disciplines. It begins not with scientists looking for evidence of dinosaur extinction, but with geophysicists looking for oil. In the late 1970s, while the Alvarez team was analyzing clay layers in Italy, two geophysicists named Antonio Camargo and Glenn Penfield were working for Pemex, Mexico's national oil company. Their job was to survey the Yucatan Peninsula, searching for geological structures that might indicate oil deposits. They were using both magnetic and gravity surveys, measurements that can reveal hidden features beneath the ground. As they analyzed their data, something strange appeared. The magnetic and gravity readings showed a massive semicircular structure centered near a small town called Chicxulub, Puerto, on the northern coast of Yucatan. The structure was enormous, extending from the land out under the waters of the Gulf of Mexico. It appeared to be a nearly perfect circle, roughly 110 miles in diameter. Penfield was intrigued. The circular shape, the size, the geological features all suggested this might be an impact crater. He presented his findings at a conference, proposing that this could be evidence of an ancient asteroid strike. But at the time, the connection to the dinosaur extinction wasn't made. Penfield couldn't get funding to drill into the structure and obtain samples that could be dated. Without that crucial evidence, his discovery languished, known to a few specialists but not widely recognized. Meanwhile, the search for the KT impact crater continued. By the late 1980s, attention had begun to focus on the Caribbean region. The pattern of debris in the boundary layer suggested the impact had occurred somewhere in or around this area. The microtectites found in boundary rocks showed a pattern of distribution that pointed toward the Gulf of Mexico and Caribbean region as a likely source. In '90, a breakthrough occurred. Alan Hildebrand, a graduate student working with his advisor William Boynton at the University of Arizona, was analyzing samples from Haiti. These samples contained shocked quartz and other impact materials, all pointing to a nearby impact site. When Hildebrand presented his findings at a conference, he caught the attention of a reporter named Carlos Byers, who remembered hearing about Penfield's circular structure off Yucatan years earlier. Byers connected Hildebrand with Penfield. Suddenly, pieces fell into place. Penfield still had access to data from the Pemex surveys, including information from drill cores that had been taken from the structure years earlier and stored in New Orleans. When these samples were analyzed, they revealed shocked minerals and other evidence of impact. The age of the rocks was determined to be approximately 66 million years old, exactly matching the age of the KT boundary. The structure buried beneath the Yucatan was the long-sought crater. It had been hidden partly beneath the land and partly beneath the ocean, covered by hundreds of feet of sediment that had accumulated over millions of years. This burial had actually helped preserve it. On land, erosion can destroy or obscure impact craters over time. But beneath layers of limestone and other sedimentary rock, the Chicxulub crater remained intact, a frozen moment of catastrophe waiting to be discovered. The crater is named after the nearby town of Chicxulub, a Mayan word often translated as tail of the devil or flea of the devil, an eerily appropriate name for the site where an object from space ended the age of dinosaurs. Penfield later joked that part of the motivation for the name was to give academics and NASA skeptics a challenging time pronouncing it, after years of having his discovery dismissed. As more data accumulated, the full scale of the Chicxulub crater became clear. The visible crater, the part that had shown up in Penfield's original surveys, was about 110 miles in diameter. But further investigation revealed this was actually an inner ring. The full crater extends much farther, with some estimates suggesting the entire disturbed area could be as much as 80 to 200 miles across. This makes Chicxulub one of the largest impact structures on Earth, comparable in size to only a handful of other ancient craters preserved on our planet's surface. The crater's structure tells the story of the impact itself. At the center is what's called a peak ring, a circular mountain range formed in the immediate aftermath of the collision. When the asteroid struck, it punched a hole deep into Earth's crust. The rock beneath, temporarily behaving almost like a liquid due to the immense pressures and energies involved, rebounded upward, forming a central peak. This peak then collapsed, falling back down, but leaving behind a raised ring of mountain peaks, all within minutes of the initial impact. Outside this peak ring lies a depression, the main bowl of the crater, now filled with sediment. Beyond that is the outer rim, marking the edge of the initial excavation zone. In some places, this rim is visible as subtle features in the landscape, though millions of years of erosion and sediment deposition have largely hidden it. Underground, the structure is clearer, visible in seismic data and drill cores as disrupted and fractured rock. In 2016, an ambitious scientific drilling project was launched to extract core samples from the Chicxulub crater's peak ring. The project involved lowering a drill through ocean waters and then through hundreds of feet of sediment to reach the rocks of the crater itself. The cores they extracted provided an unprecedented look at the impact site, offering detailed evidence of what happened on that catastrophic day 6 million years ago. The rocks told a story of unimaginable violence. They found granite that had been lifted from deep within Earth's crust, rock that should have been several miles below the surface now located much higher, testament to the explosive forces at work. They found evidence of extreme temperatures with minerals that had been melted and resolidified. They found impact glass, formed when rock was vaporized and then cooled so rapidly it turned to glass rather than crystallizing normally. Most importantly, they found iridium. Right at the boundary between the impact breccia, Sormera, the jumbled mess of broken rock created by the collision, and the sediments that accumulated in the hours and days afterward, there was a spike in iridium concentration. This was the smoking gun, the final proof linking the crater directly to the global iridium layer found at the KT boundary worldwide. The discovery of Chicxulub crater transformed our understanding of Earth's history. It provided incontrovertible evidence that catastrophic events can and do occur, reshaping life on our planet in geologically brief moments. It showed that the history of life on Earth is not just a story of gradual evolution and adaptation, but also includes moments of dramatic, violent change driven by forces beyond the planet itself. But identifying the crater was just the beginning. Understanding what happened next Reconstructing the sequence of events that led from impact to extinction required combining evidence from geology, paleontology, climate science, and physics. It meant building computer models of the impact and its effects. It meant looking at the fossil record in even greater detail, trying to understand exactly how quickly different organisms went extinct and which ones managed to survive. The story that emerged is one of the most dramatic in the history of science, a tale of cosmic violence meeting biological complexity, of a world destroyed and remade in a span of time incomprehensibly brief compared to the millions of years it took for that world to develop in the first place. The Day of Impact, the object that ended the age of dinosaurs, began its final journey long before that catastrophic day X million years ago. It formed in the early days of our solar system, roughly 4.5 billion years ago, when swirling clouds of dust and gas were condensing into the sun and planets. Not everything became part of a planet. Between Mars and Jupiter, in a region where gravitational forces prevented a planet from forming, countless rocky bodies remained, ranging from tiny pebbles to objects hundreds of miles across. This is the asteroid belt, home to remnants of our solar system's formation. Recent analysis of the chemical composition of the Chicxulub impactor suggests it was likely a carbonaceous chondrite, a type of asteroid that often contains water, clay minerals, and organic compounds. These are among the most primitive objects in the solar system, relatively unchanged since their formation. The asteroid that would eventually strike Earth was approximately 6 to 9 miles in diameter, a mountain of rock and metal traveling through space on an orbit that, for billions of years, kept it safely away from Earth. But orbits change. Gravitational interactions with Jupiter and other planets can perturb asteroid trajectories over millions of years. Sometimes, these perturbations send an asteroid on a new path, one that crosses Earth's orbit. Most of the time, Earth and the asteroid are in different parts of their orbits when this crossing occurs, and nothing happens. But occasionally, tragically, they arrive at the crossing point at the same moment. On that day, 66 million years ago, an asteroid was approaching Earth at a relative velocity of approximately 12 to 20 miles per second, roughly 40,000 to 70,000 miles per hour. To put this in perspective, a rifle bullet travels at about 2,000 miles per hour. The asteroid was moving at speeds that make such comparisons almost meaningless, velocities at which solid rock behaves in ways that seem impossible. As it entered Earth's atmosphere, the asteroid's enormous kinetic energy began converting to other forms. The air in front of it compressed and heated to temperatures hotter than the surface of the sun. But the asteroid was moving so fast that it punched through the atmosphere in just a few seconds. There was no slow-motion entry, no gradual descent. The atmosphere barely had an anemone, time to respond before the asteroid had passed through it and struck the surface. The impact occurred in a shallow sea off what is now Mexico's Yucatan Peninsula. The asteroid hit at an angle of approximately 60 degrees from horizontal, approaching from the northeast. This angle, as researchers later determined, was particularly unfortunate. A more vertical impact might have sent more material straight up into space. A more oblique impact might have caused the asteroid to skip off the atmosphere or lose more of its energy before striking. But at 60 degrees, the impact was optimized to send vast quantities of debris into the upper atmosphere, while still delivering its full energy to Earth's surface. The moment of impact lasted only a few seconds, but those seconds contained violence on a scale difficult to comprehend. The asteroid struck with the energy equivalent to roughly 100 million megatons of TNT, more than 1 billion times the energy of the atomic bomb dropped on Hiroshima. This is an abstraction, a number too large to truly grasp, but the effects were terrifyingly real. The first instant of contact created a shock wave that vaporized the entire asteroid and a vast volume of rock beneath and around the impact site. Temperatures reached tens of thousands of degrees. Rock simply ceased to exist as solid matter, transformed into superheated plasma and vapor. The crater began to form, punching down through layers of limestone, through ancient sediments, into the granite bedrock beneath. Within seconds, the crater had reached its maximum depth, perhaps 15 to 20 miles into Earth's crust. Then came the rebound. The rock beneath, though solid on human timescales, behaved like a liquid under these extreme conditions. It surged upward, forming a central peak that may have briefly reached heights of 6 to 10 miles above the original surface. This peak collapsed back down, settling into the ring of mountains we now see in seismic data as the peak ring. Meanwhile, energy was radiating outward from the impact site. Earthquakes of magnitude 10 or greater, far beyond anything in recorded human history, shook the planet. These weren't localized tremors, but global seismic events. The ground undulated in waves hundreds of feet high, solid rock flowing like water. Buildings, if any had existed, would have been instantly obliterated. Forests were flattened. Animals within hundreds of miles were killed instantly before they could even react to what was happening. The impact generated a thermal pulse that radiated outward at the speed of light. For a brief moment, anyone looking toward the impact site from thousands of miles away would have seen a light brighter than the sun. This pulse of thermal radiation set fires across an enormous area. Everything flammable, within perhaps 1,000 miles, burst into flames. Trees, plants, animals, anything organic was incinerated. The fires generated their own winds, creating firestorms that fed on themselves, reaching temperatures hot enough to melt rock. Massive tsunamis radiated from the impact site. The asteroid struck in shallow water, perhaps a few hundred feet deep. The impact vaporized this water along with the rock, but surrounding water rushed in to fill the crater, only to be blasted back out as the rebound occurred. Waves hundreds of feet high, possibly over 1,000 feet in some areas, raced across the ocean at hundreds of miles per hour. These waves crashed into coastlines around the Gulf of Mexico and Caribbean, reaching as far as modern Texas, Florida, and deep into the interior of the Americas where ancient seaways existed. The evidence for these tsunamis can be found in geological deposits. In places that were coastal areas 66 million years ago, there are thick layers of jumbled sediment containing everything from sand to boulders, mixed together chaotically. Some deposits show ripple marks and flow patterns characteristic of massive water movement. Blend in with these sediments are spherules, tiny glass beads formed from molten rock ejected by the impact, proving these deposits date to the exact moment of the catastrophe. But perhaps the most devastating effect of the impact was what it threw into the sky. Trillions of tons of rock, pulverized into dust, and microscopic particles were ejected into the atmosphere. Some of this material, traveling at escape velocity, left Earth entirely, flung into space by the violence of the impact. But most of it went up and then came back down, spreading across the globe. The larger chunks of rock, still glowing hot from the impact, re-entered the atmosphere around the world. As they did, they created a second pulse of thermal radiation, this one global in extent. Anyone looking up would have seen the sky filled with what appeared to be meteors, thousands upon thousands of streaks of light, all falling at once. But these weren't harmless shooting stars. They were pieces of Mexico falling back to Earth, and they were heating the atmosphere as they fell. Some researchers believe this re-entry heating could have been intense enough to cause global ignition of vegetation. The sky itself became a broiler, radiating enough heat to set fires anywhere on Earth that had a direct view of the upper atmosphere. Forests around the world may have burst into flames simultaneously, in regions thousands of miles from the impact site that had felt no direct effects of the collision itself. In the fossil record, there's evidence for this global fire. The KT boundary layer contains vast amounts of soot, far more than could have been produced by fires near the impact site alone. This soot layer is found worldwide, suggesting that wildfires raged across multiple continents. The scale of these fires would have been unprecedented, burning through ecosystems that had never experienced such devastation, releasing vast quantities of smoke and carbon dioxide into the already debris-filled atmosphere. And in the Gulf of Mexico itself, the immediate aftermath was apocalyptic. When researchers drilled into the Chicxulub crater in 2016, they found charcoal in the rock layers deposited in the hours after impact. Trees and plants had been flash burned, their carbonized remains swept into the crater by returning waters. The cores showed a sequence of events: impact debris, then a jumbled mix of impact material and ocean sediment brought in by tsunamis. Then finer sediments deposited as the waters calmed, all within the first day. Life within hundreds or even thousands of miles of the impact site was simply erased. There were no survivors in the immediate area. Everything was incinerated, crushed, vaporized, or drowned. But the direct effects of the impact, devastating as they were limited by geography. An animal living in Australia or Africa would have been safe from the earthquakes, the heat pulse, the tsunamis. They might have noticed strange lights in the sky, might have felt the ground tremble slightly, but they would have survived the day. The problem was, the catastrophe was just beginning. The true killer was what came next, in the days, weeks, months, and years following the impact. It wasn't the immediate violence that caused the mass extinction. It was the long, slow collapse of Earth's ecosystems under conditions that made survival nearly impossible for most forms of life. The long dark, as the dust settled after the initial impact, quite literally, Earth found itself wrapped in a shroud that would last for years. The bark and dust ejected by the Chicxulub impact didn't simply fall back to the ground immediately. The finest particles, microscopic grains of pulverized rock, remained suspended in the upper atmosphere, forming a global cloud that encircled the planet. Imagine, for a moment, what it must have looked like. In the first hours after impact, the sky would have been filled with debris, glowing with re-entry heat, creating a hellish light that ignited fires worldwide. But as this initial fury subsided, as the larger pieces fell back to Earth and the fires exhausted their fuel, a different kind of darkness settled in. The sky would have turned brown, then gray, then an oppressive, uniform darkness. The sun, which had shone on Earth for billions of years, providing the energy that powered nearly all life on the planet, was blocked. This is what scientists call impact winter, and its effects would have been catastrophic. The dust particles were small enough to stay airborne for months or even years, yet large enough to effectively block sunlight. Recent studies suggest that the amount of fine silicate dust ejected by the impact could have reduced sunlight reaching Earth's surface by as much as 80 to 90%. In some regions, it might have been even worse, with virtually no light penetrating the dust cloud. Photosynthesis, the process by which plants convert sunlight into chemical energy, ground to a near halt. This didn't happen immediately. Plants have reserves of energy stored in their tissues. They can survive periods of low light. But as days turned to weeks, and weeks turned to months, these reserves were depleted. Plants began to die, starting with those species that required the most light and spreading through ecosystems like a slow-motion wave of death. The first to go would have been the phytoplankton in the oceans, microscopic photosynthetic organisms that form the base of marine food chains. These organisms have short lifespans and limited energy reserves. Within weeks of the impact, their populations would have crashed catastrophically. This collapse would have rippled up through the food web. Zooplankton that fed on phytoplankton starved. Small fish that ate zooplankton starved. Larger fish, marine reptiles, and all the other predators in the ocean faced the same fate. On land, the die-off proceeded more slowly but was no less catastrophic. Trees could survive longer than small plants, using energy stored in their roots and trunks. But as the darkness persisted, even the largest trees began to fail. Leaves fell. Photosynthesis ceased. The trees drew on their reserves, but these could only last so long. Forests around the world began to die, leaving behind a landscape of skeletal trees under dark skies. Herbivorous dinosaurs faced an impossible situation. The plants they depended on were dying. Some might have survived by eating bark, roots, or dead plant material. But these were poor substitutes for fresh vegetation, providing less nutrition and requiring more energy to digest. Large herbivores, with their enormous daily food requirements, were particularly vulnerable. A full-grown sauropod, or hadrosaur, needed to eat hundreds of pounds of plant material every day. As plants died, these requirements became impossible to meet. The cooling that accompanied the darkness made conditions even worse. Without sunlight warming the surface, temperatures plummeted. The late Cretaceous world had been warm, with tropical and subtropical conditions extending far beyond their current range. Many species were adapted to this warmth and had little tolerance for cold. As temperatures dropped, many organisms found themselves in conditions they simply couldn't survive. The temperature drop wasn't uniform. Coastal areas, moderated by the ocean's thermal mass, would have stayed warmer than inland regions. Tropical areas, receiving more sunlight even under the dust cloud, would have suffered less cooling than higher latitudes. These regional differences created temperature gradients far steeper than organisms were used to, adding thermal stress to an already catastrophic situation. For carnivorous dinosaurs, the collapse of herbivore populations spelled doom. At first, there would have been plenty to eat. The dying herbivores provided carrion, more food than the predators could possibly consume. But this abundance was temporary. As herbivore populations crashed, the food supply for carnivores evaporated. Predators began starving, competing desperately for the dwindling remains of their former prey. The flying pterosaurs faced particular challenges. Their high-energy lifestyle, sustained by constant foraging, became unsustainable as their prey disappeared. Small animals, insects, fish, all were impacted by the collapse of photosynthesis-based food chains. Pterosaurs, with their massive wingspans and energy-intensive flight, needed constant feeding. As food became scarce, they simply couldn't maintain the energy balance necessary for survival. Studies of the impact winter scenario suggest the darkness could have persisted for months to potentially several years. Different models give different estimates depending on assumptions about particle sizes, atmospheric circulation, and other factors. But the consensus is that the period of significantly reduced sunlight lasted long enough to break the back of terrestrial ecosystems worldwide. Recent research has added another frightening dimension to this scenario. In addition to rock dust, the impact ejected vast quantities of sulfur into the atmosphere. The Yucatan Peninsula is rich in sulfur-containing rocks, particularly anhydrite, a mineral composed of calcium sulfate. When the asteroid struck, it vaporized enormous volumes of this rock, sending sulfur compounds into the atmosphere. Sulfur dioxide combines with water vapor to form sulfuric acid. This acid then forms tiny droplets, aerosols that can remain suspended in the atmosphere for years. These aerosols are even more effective than dust at blocking sunlight. They're also reflective, bouncing solar radiation back into space before it can warm the surface. The combination of rock dust and sulfate aerosols would have created an even darker, colder world than dust alone could produce. Intriguingly, drill cores from Chicxulub show a notable absence of sulfur in the impact structure itself, despite the I region being rich in sulfur-bearing rocks. This absence suggests that the sulfur was vaporized and ejected into the atmosphere, rather than being incorporated into the impact melt or breccia. In other words, the impact hit in almost exactly the wrong place, maximizing the climate-altering potential of the collision. As the months passed under dark skies, the extinction accelerated. Species that had initially survived the impact found themselves in a world that could no longer support them. Food chains collapsed from the bottom up. Plants died. Herbivores starved. Carnivores followed. In the oceans, the same pattern played out. Plankton died. Filter feeders starved. The complex marine ecosystems built up over millions of years came apart in a matter of years. The extinction wasn't instantaneous or uniform. Some regions suffered more than others. Some ecosystems proved more resilient than others. In areas where plants managed to survive in reduced numbers, some herbivores clung to existence. In the oceans, organisms that could feed on detritus, on dead organic matter, had an advantage over those that required live prey. But everywhere the same pattern played out. Populations crashed, species disappeared, ecosystems simplified. Eventually, the dust began to settle. The finest particles, those that had stayed aloft the longest, finally fell to Earth. Sunlight, faint at first but growing stronger, began to penetrate the atmosphere. Plants, or at least those species that had managed to survive in some form, began to grow again. But by then, the damage was done. The world that emerged from the darkness was fundamentally different from the world that had existed before the impact. Chemical catastrophe. The darkness and cold of impact winter were devastating enough, but they weren't the only mechanisms by which the Chicxulub impact reshaped Earth's environment. The chemistry of the planet's atmosphere and oceans underwent dramatic shifts, creating conditions toxic to many forms of life and making recovery even more difficult for those species that initially survived. We've already mentioned the sulfur dioxide ejected by the impact. This gas didn't just block sunlight. When it combined with water in the atmosphere, it formed sulfuric acid. This acid then fell as rain, poisoning freshwater systems and acidifying soils. Acid rain on a global scale would have burned the leaves of surviving plants, damaged the gills of fish, and altered soil chemistry in ways that made it harder for plants to grow even after sunlight returned. The acidity of rain in the aftermath of the impact would have been far beyond anything seen in modern times, even in areas affected by industrial pollution. The sheer quantity of sulfur dioxide injected into the atmosphere was staggering, potentially hundreds of billions of tons. This created rainfall with pH levels that could have approached that of battery acid in some areas, particularly those near the impact site or under the main trajectory of the stratospheric sulfate cloud. The oceans didn't escape this chemical assault. Recent research has provided compelling evidence for rapid and severe ocean acidification in the immediate aftermath of the impact. When acid rain falls into the ocean, it lowers the pH of surface waters. More importantly, the vast quantities of carbon dioxide released by the impact, from vaporized carbonate-free rocks and from global wildfires, dissolved into the ocean, further decreasing pH. Ocean acidification is particularly devastating for organisms that build shells or skeletons from calcium carbonate. In acidic water, calcium carbonate dissolves more easily, making it harder for organisms to construct and maintain their protective structures. This would have been catastrophic for the countless species of shell-building plankton, for ammonites with their beautiful spiral shells, for mollusks, for coral, and for many other marine invertebrates. The fossil record supports this scenario. Above the KT boundary, there's a dramatic reduction in the diversity and abundance of foraminifera, microscopic shell-building organisms that had been enormously successful and diverse in Cretaceous oceans. The species that do appear in rocks immediately above the boundary are often simple forms with smaller, less elaborate shells, suggesting that conditions favored organisms that minimize their calcium carbonate requirements. The extinction of ammonites, one of the most successful groups of marine predators for hundreds of millions of years, may be directly linked to ocean acidification. These creatures, relatives of modern squids and octopi, but with external chambered shells, were unable to survive in the changed ocean chemistry. Every single species of ammonite went extinct at the KT boundary. Their only relatives to survive were nautiloids and coleoids, the shell-less or internal-shelled cephalopods that didn't rely as heavily on calcium carbonate structures. The impact also released vast quantities of carbon in the form of carbon dioxide and carbon monoxide. The fires that raged worldwide released carbon from burning vegetation. The vaporization of carbonate rocks at the impact site released even more. Some estimates suggest that the total amount of carbon dioxide released into the atmosphere may have been comparable to what humans might release over several thousand years at current rates of fossil fuel burning, except this release happened essentially instantaneously. In the long term, after the dust and sulfate aerosols settled out of the atmosphere, this carbon dioxide would have caused greenhouse warming. This created a climate whiplash effect, global cooling followed by global warming, that further stressed survivors trying to recover from the initial impact. Species that had adapted to cope with the cold found themselves facing rising temperatures. Ocean chemistry, after swinging toward acidic, had to readjust to new levels of dissolved carbon dioxide. Another toxic component released by the impact was mercury. Recent studies have found elevated mercury concentrations in rock layers corresponding to the KT boundary. Mercury is often associated with volcanic activity, but it's also present in some types of rock and can be mobilized by the extreme temperatures of an impact. Mercury is toxic to many forms of life, affecting nervous systems and accumulating in food chains. Elevated mercury levels would have added another stressor to organisms already struggling with darkness, cold, acid rain, and food scarcity. The impact may have also caused ozone layer depletion. The heat from the impact and from re-entering debris could have generated nitrogen oxides through reactions between nitrogen and oxygen in the atmosphere. these nitrogen oxides are known to destroy ozone. With a depleted ozone layer, more ultraviolet radiation from the sun would have reached Earth's surface. This UV radiation can damage DNA, harm plant tissues, and kill plankton in surface waters. Organisms that survived the initial darkness would have then faced increased UV radiation as skies cleared, creating yet another obstacle to recovery. In terrestrial ecosystems, the chemistry of soil was profoundly altered. The combination of acid rain, ash from global wildfires, and dust from the impact changed soil pH and nutrient availability. Plants trying to recolonize affected areas would have found soils that were very different from what existed before the impact. Some nutrients might have been more available, leached out of ash and rock dust, but others would have been locked up in insoluble forms or washed away entirely. Nitrogen fixation, the process by which certain bacteria convert atmospheric nitrogen into forms usable by plants, may have been disrupted. These bacteria are sensitive to environmental conditions. The extreme changes following the impact could have killed many nitrogen-fixing bacteria, or created conditions where they couldn't function effectively. This would have made it harder for plant communities to recover, as nitrogen is often a limiting nutrient in terrestrial ecosystems. The combination of all these chemical changes created a planet that was not just dark and cold, but also toxic in multiple ways. Organisms that might have survived one or two of these stressors found themselves facing a suite of challenges that together were insurmountable. The chemical catastrophe compounded the physical catastrophe, ensuring that recovery would be slow and that many lineages would not survive. As evidence for these various chemical effects has accumulated, it's become clear that the Chicxulub impact didn't just hit Earth like a giant hammer. It rewrote the chemistry of the entire planet's surface environment in ways that persisted for thousands to millions of years. The world that eventually recovered from this catastrophe was chemically different from the world that existed before, with profound implications for which organisms could thrive in the new conditions. The Deccan Traps Controversy. As evidence mounted for the asteroid impact as the primary cause of the dinosaur extinction, another geological feature was demanding attention from scientists. In western India lies a vast region called the Deccan Traps, a massive plateau built from layer upon layer of ancient lava flows. These aren't just large, they're enormous, one of the largest volcanic features on Earth. In some areas, the basalt layers are over 2 miles thick. The timing of the Deccan Traps eruptions is striking. They occurred right around the KT boundary 66 million years ago, the same time as the Chicxulub impact. For years, this coincidence has fueled debate among scientists. Were the Deccan Traps eruptions responsible for the extinction? Did they work together with the impact? Or were they largely irrelevant, a geological sideshow to the main event? The term traps comes from the Swedish word for stairs, trappa, referring to the step-like topography created by the layered lava flows. When lava erupts and flows across the land, it cools and hardens into basalt. Repeated eruptions build up layers, creating the distinctive terraced appearance visible in the landscape today. The Deccan Traps represent multiple eruption episodes over hundreds of thousands of years, each pouring out vast quantities of lava. Volcanic eruptions on this scale don't just produce lava, they release enormous quantities of gases into the atmosphere. Carbon dioxide, sulfur dioxide, chlorine, fluorine, and other volatiles. When these gases reach the upper atmosphere, they can affect climate globally. Sulfur dioxide, in particular, forms aerosols that cool the planet by reflecting sunlight, similar to the effect of the dust from the Chicxulub impact. Carbon dioxide, meanwhile, is a greenhouse gas that causes warming. Some scientists, most notably Gerta Keller of Princeton University, have argued for decades that the Deccan Traps volcanism was the primary driver of the KT extinction. They point to evidence that ecosystems were already stressed before the impact, with some species declining in diversity. They argue that the volcanic gases would have created climate fluctuations, swinging between cooling from sulfur dioxide and warming from carbon dioxide, that would have been devastating to life. The challenge in evaluating this hypothesis has been precisely dating when the eruptions occurred. Volcanic rocks are difficult to date with high precision, especially rocks as old as those in the Deccan Traps. For years, age estimates had uncertainties of hundreds of thousands or even millions of years, making it impossible to determine whether the bulk of the eruptions occurred before, during, or after the extinction event. Recent advances in geochronology, particularly using uranium-laid dating of tiny zircon crystals found in ash layers between lava flows, have provided much more precise dates. Two independent research teams, one from the University of California, Berkeley, and one from Princeton, traveled to India to collect samples and analyze the timing of the Deccan eruptions. Their results, published in 2019, represent some of the most precise dating ever achieved for these volcanic rocks. What they found was fascinating and complex. The Deccan Traps didn't erupt continuously. Instead, there were four main pulses of volcanism, periods of intense activity separated by quieter intervals. One of these pulses occurred in the few 100,000 years before the Chicxulub impact. Another major pulse occurred right around the time of the impact and continued for several 100,000 years afterward. This timing suggests that both the volcanism and the impact may have contributed to the extinction, though in different ways and at different times. The volcanism before the impact may have stressed ecosystems, reducing diversity and making species more vulnerable. The impact then delivered a knockout blow, and the continued volcanism after the impact may have delayed recovery, releasing gases that maintained challenging environmental conditions for hundreds of thousands of years after the initial catastrophe. Interestingly, the two research teams found evidence that the impact itself may have affected the Deccan volcanism. The pulse of eruptions right around the time of the impact was more voluminous and more rapid than earlier pulses. Some researchers suggest that seismic waves from the impact, traveling through Earth's interior, could have triggered increased volcanic activity in already active volcanic systems around the world, particularly in the Deccan region, where large volumes of magma were already present beneath the surface. The mechanism by which an impact might trigger volcanic eruptions is still debated, but it's physically plausible. The seismic energy from a massive impact could jostle magma chambers, causing eruptions in systems that were already close to erupting. It's also possible that the pressure waves traveling through the planet could open new pathways for magma to reach the surface, or destabilize partially molten rock in the mantle beneath volcanic regions. Recent modeling studies have tried to disentangle the relative contributions of the impact and the volcanism. One approach uses machine learning to analyze the geochemical record, looking at carbon isotopes, oxygen isotopes, and other tracers of environmental change in marine sediments spanning the KT boundary. These models attempt to determine what combination of volcanic gas release and impact effects best explains the observed patterns in the rock record. Results from these models are somewhat controversial, but they suggest that the Deccan Trap's volcanism alone could have been sufficient to cause significant environmental stress and extinctions, possibly even a mass extinction. However, the pattern of extinction in the fossil record, particularly the sudden disappearance of many species right at the KT boundary layer, seems to require the sudden, catastrophic effects of an impact rather than the more gradual environmental changes caused by volcanism. Perhaps the most likely scenario is that the extinction was caused by a combination of factors. The Deccan Trap's volcanism, erupting for hundreds of thousands of years before the impact, would have caused climate instability and ecosystem stress. Species already stressed by volcanic gases and climate fluctuations would have been more vulnerable when the asteroid struck. The impact then caused the actual mass extinction event, the sudden darkness and cold that broke ecosystems globally, and finally, continued volcanism after the impact delayed recovery, maintaining harsh conditions and preventing the rapid rebound of life. This 1-2 punch hypothesis, or perhaps more accurately a 1-2-3 punch hypothesis, accounts for evidence of both gradual stress and sudden catastrophe. It explains why some species seem to have been declining before the boundary, while others disappeared suddenly at the boundary itself. It also explains the slow recovery after the extinction, with ecosystems taking hundreds of thousands to millions of years to fully recover their pre-extinction diversity. The debate over the Deccan Traps continues among scientists. New evidence is still being gathered. New dating techniques are being developed, and our understanding of how volcanic gases affect global climate continues to improve. But there's growing consensus that while the impact was likely the immediate cause of the mass extinction, the volcanic activity was significant and may have made the impact more devastating than it would have been otherwise. Understanding the interplay between these two catastrophes is important, not just for understanding what happened X million years ago, but for understanding how Earth's climate system responds to massive perturbations. The KT extinction represents one of the best documented cases of rapid, extreme climate change in Earth's history. The lessons learned from studying this event inform our understanding of climate change more broadly, including modern human-caused climate change, which, while different in kind, involves in similarly rapid alterations to atmospheric chemistry. Who survived and why? In the aftermath of the Chicxulub impact and the environmental catastrophes it triggered, life on Earth was decimated but not entirely destroyed. Roughly 75% of all species went extinct, but that means 25% survived. Understanding who survived and why reveals as much about the nature of the catastrophe as understanding who went extinct. The most famous survivors are the birds. Birds are dinosaurs, the only dinosaurs that made it through the KT boundary. But they weren't just any dinosaurs. The birds that survived were relatively small, mostly ground-dwelling species that could survive on seeds, insects, and other food sources that remained available even when large herbivores and their predators were dying out. In the immediate aftermath of the impact, large body size was a death sentence for terrestrial vertebrates. The fossil record shows a striking pattern. No land-dwelling animals larger than about 55 pounds survived the KT extinction. This size threshold makes sense when you consider the environmental conditions. Larger animals need more food, have slower reproductive rates, and are less able to take shelter. As food chains collapsed and temperatures swung wildly, large animals simply couldn't meet their energy requirements or reproduce fast enough to maintain populations. Small birds that could eat seeds had a crucial advantage. Seeds represent plant energy stored in a compact, durable form. Many seeds can survive for years in soil, dormant but viable. Even as adult plants died in the darkness of impact winter, vast numbers of seeds remained, buried in soil or lying on the ground. Small birds that could exploit this food source had something to eat even when fresh vegetation was unavailable. Ground-dwelling habits also conferred advantages. Birds that lived in trees would have faced challenges as forest boyd died. But ground-dwelling birds could survive in a wider range of conditions. They could shelter in burrows or under debris. They could move to find food and water. They weren't dependent on forest canopy that was rapidly disappearing. The bird lineages that made it through the KT boundary subsequently diversified into the approximately 10,000 species we see today. This is called adaptive radiation, the rapid diversification of a lineage into many new species that exploit different ecological niches. The extinction opened up those niches, creating opportunities for survivors to evolve and spread. Mammals were also survivors, and for many of the same reasons as birds. They were small. Most species weighed less than a few pounds. They were often burrowing animals, spending time underground where they were insulated from temperature extremes and protected from the initial heat pulse of the impact. Many were omnivores or insectivores, with flexible diets that could adapt to changing food availability. The ability to burrow was particularly important for survival. Underground chambers maintained relatively stable temperatures even as surface temperatures dropped during impact winter. Burrows provided protection from wildfires, from the heat pulse of re-entering debris, from predators. Animals that could retreat underground to wait out the worst conditions had a significant advantage over those that couldn't. Crocodilians survived the extinction remarkably well. These animals, though related to dinosaurs, had characteristics that made them resilient. They can go for long periods without eating, sometimes months or even years, living off stored fat and energy. They can survive in a wide range of water conditions. Many species can move between freshwater and saltwater. This flexibility allowed them to survive as ecosystems collapsed around them. Turtles also came through the extinction with relatively little damage. Like crocodilians, turtles can survive long periods without food. Many species can enter a state of dormancy, slowing their metabolism to minimal levels. Their shells provide protection from predators and environmental hazards. Aquatic turtles living in rivers and ponds would have been somewhat buffered from temperature extremes and may have had access to food sources like aquatic plants, fish, and invertebrates that survived the impact. In the oceans, the extinction patterns were more complex. Some groups were devastated. All mosasaurs and plesiosaurs went extinct, as did the ammonites. But other groups survived with little impact. Sharks made it through relatively unscathed. Most groups of bony fish survived, though there were extinctions within these groups. Some marine reptiles, particularly sea turtles, survived. The pattern in the oceans seems related to food sources. Organisms that depended on photosynthesis-based food chains, particularly those feeding on plankton, were hit hard. But organisms that could feed on detritus, on dead organic matter, or that lived in deep ocean environments where they weren't dependent on surface productivity, had better survival rates. Freshwater ecosystems showed surprisingly high survival rates. Fish, amphibians, and invertebrates living in rivers, lakes, and ponds seem to have come through the extinction with less damage than might be expected. This may relate to the nature of freshwater food webs. In many freshwater systems, organic matter washed in from land forms an important food source. Even when photosynthesis was reduced, this detritus-based food web could continue functioning, supporting populations of fish, insects, and other organisms. Plants showed interesting patterns of survival and extinction. Some groups, particularly seed-producing plants, survived well. As mentioned earlier, seeds can remain dormant for long periods, allowing these plants to wait out the bad conditions. Ferns, which reproduce via spores and can colonize disturbed ground rapidly, show a dramatic increase in the fossil record right after the KT boundary. This fern spike is found worldwide and represents the recolonization of devastated landscapes by these opportunistic plants. Geographic location also played a role in survival. Organisms living in polar regions, already adapted to long periods of darkness and cold during winter, may have been better prepared for impact winter than those from tropical regions. Species with broad geographic ranges had better chances of surviving than those with limited ranges because populations in different regions might experience different levels of impact effects. The role of chance should not be underestimated. Evolution doesn't prepare organisms for catastrophes they've never experienced before. The characteristics that allowed survival of the KT extinction were not adaptations to asteroid impacts. They were pre-existing features that happened to be useful under the extreme conditions that followed. In that sense, which lineages survived was partly a matter of luck, being in the right place at the right time with the right characteristics. This randomness in survival has profound implications. The modern world, including humans, exists because our mammalian ancestors happened to have characteristics that allowed them to survive a catastrophe they could not have anticipated. If the circumstances had been slightly different, if the impact had occurred at a different location or at a different angle, the survival patterns might have been different, and the subsequent history of life on Earth would have unfolded in completely different ways. The recovery. The world that emerged from the darkness of impact winter was radically simplified compared to the complex ecosystems that existed before. But it wasn't empty. Survivors clung to existence in a damaged but not dead world, and slowly, over thousands and millions of years, life began to rebuild. The immediate aftermath of the extinction, the first few thousand years, was a time of ecological chaos. With most large herbivores and carnivores gone, the structure of terrestrial food webs was fundamentally altered. The survivors were small animals, mainly scavengers and omnivores, living in a world of dead trees and reduced plant productivity. Productivity is a measure of how much energy flows through an ecosystem, and in post-impact Earth, productivity was dramatically lower than it had been. The fern spike visible in the fossil record represents the first stage of recovery. Ferns colonized the devastated landscapes, creating a green cover but not yet recreating the complex forest ecosystems that had existed before. These early pioneer communities were simple, with low diversity and limited vertical structure. There were no tall trees, no layered canopy, no complex understory. Just ferns and other quickly colonizing plants covering the ground that had been burned or buried under impact debris. This stage lasted for tens of thousands of years. Gradually, other plants began to return. Seeds that had lain dormant sprouted. Some trees regenerated from roots that had survived underground. Wind and water carried seeds from areas that had been less affected. The plant communities slowly diversified, though they remained less diverse than those of the Cretaceous for a long time. Animal communities recovered in tandem with plant communities. As plant productivity increased, populations of herbivorous insects, small mammals, and birds expanded. These herbivores supported small carnivores, and gradually food webs began to rebuild their complexity. But this recovery was slow, measured in evolutionary time rather than human time. The fossil record in the Paleocene, the first epoch after the Cretaceous, shows a world that looked very different from the late Cretaceous. Mammal diversity increased rapidly as these previously marginal creatures exploited the niches left vacant by dinosaur extinction. Within a few million years of the impact, mammals had diversified into many of the major groups we see today: primates, ungulates, carnivores, and many others. This radiation was not uniform or smooth. Early Paleocene mammals were still relatively small, most weighing less than 20 or 30 pounds. It took roughly 10 million years for large mammals, comparable in size to the largest dinosaurs, to evolve. This delay might reflect the time needed for ecosystems to rebuild enough productivity to support large herbivores, or it might reflect evolutionary constraints on how quickly body size can increase. In the oceans, recovery followed different patterns. Plankton communities rebounded relatively quickly, within hundreds of thousands of years. These organisms have short generation times and high reproduction rates, allowing rapid evolution and population growth when conditions improve. But the recovery of plankton diversity took longer. It was millions of years before marine plankton communities reached the diversity levels seen before the extinction. Larger marine animals took even longer to recover. With mosasaurs and plesiosaurs extinct, new marine predators had to evolve. This eventually happened, with sharks expanding into some niches and marine mammals later becoming dominant predators in many ocean ecosystems. But this transition took tens of millions of years. The extinction and subsequent recovery had long-lasting effects on the structure of terrestrial ecosystems. Before the KT extinction, large herbivores were reptiles, animals that grew continuously throughout life and could reach enormous sizes. After the extinction, large herbivores were mammals, which have determinate growth, reaching adult size, and then stopping. This shift changed the dynamics of plant-herbivore interactions in ways that persist to this day. The recovery period was also marked by climate change. The initial impact, winter gave way to warmer conditions, partly due to the carbon dioxide released by the Deccan traps and by the impact itself. The early Paleocene was quite warm, with tropical conditions extending far into higher latitudes. This warmth, combined with the open niches left by extinction, may have facilitated the rapid diversification of surviving lineages. One of the most striking aspects of post-extinction recovery is how long it takes. While life rebounds relatively quickly in terms of population abundance and coverage of the planet, full recovery of biodiversity takes much longer. Studies of the fossil record suggest it took at least 5 to 10 million years for terrestrial ecosystems to recover diversity levels comparable to those before the extinction. Marine ecosystems took similar amounts of time. This slow recovery reflects fundamental aspects of how ecosystems and evolution work. Species don't just pop into existence to fill empty niches. They evolve from existing species, and evolution takes time, requiring many generations for new species to arise. Complex ecological interactions. The relationships between predators and prey, between plants and pollinators, between hosts and parasites, take even longer to develop. The world that eventually emerged, the Cenozoic era that continues to the present, was fundamentally shaped by the KT extinction. The rise of mammals, including eventually primates and humans, was possible only because dinosaurs were removed from terrestrial ecosystems. Birds, the surviving dinosaurs, diversified into the skies and many terrestrial niches. Flowering plants continued their diversification, eventually coming to dominate terrestrial plant communities. In many ways, we still live in the post-extinction world. The extinction, 66 million years ago, reset the trajectory of life on Earth, removing dominant groups and allowing previously marginal ones to rise to prominence. Every ecosystem around us, every species we share the planet with, has been shaped by events that occurred on that day when an asteroid struck the Yucatan Peninsula. The recovery also teaches us something profound about resilience. Life is remarkably persistent. Even after a catastrophe that killed 3/4 of all species that darkened the sky for years, that made Earth nearly uninhabitable for many forms of life, organisms found ways to survive and eventually thrive. The mechanisms of evolution, combined with the inherent diversity of life, provide a kind of insurance against extinction. As long as some survive, recovery is possible, and even if it takes millions of years. But recovery doesn't mean returning to the previous state. The dinosaurs never came back, except in the form of birds. The lost species are lost forever. What emerged was not a restoration, but a new creation, built from the surviving pieces, but forming patterns never seen before. This is the nature of mass extinctions. They're irreversible transformations that redirect the entire future of life on the planet. Modern understanding. Today, more than 40 years after the Alvarez team first proposed the asteroid impact hypothesis, the scientific consensus has solidified around the impact as the primary cause of the KT extinction. The evidence is overwhelming. The global iridium layer, shocked quartz, microtectites, the Chicxulub crater itself, and the precise timing of all these features matching the extinction event in the fossil record. In 2010, an international panel of 41 experts from multiple disciplines reviewed all available evidence and concluded that the Chicxulub impact was indeed the cause of the mass extinction. This level of scientific consensus is rare and represents a remarkable convergence of evidence from geology, paleontology, geochemistry, and physics. But consensus doesn't mean we understand everything. Many questions remain about the exact sequence of events, the relative importance of different killing mechanisms, and the details of how different species and ecosystems responded. Modern research continues to refine our understanding through new discoveries and new analytical techniques. One area of active research involves drilling into the Chicxulub crater itself. The 2016 drilling expedition that extracted cores from the peak ring has provided unprecedented samples from the impact structure. Analysis of these cores continues, revealing new details about the impact, the rock layers involved, and the immediate aftermath. One discovery from these cores particularly captivated scientists. In the rock layers deposited just hours to days after the impact, they found evidence that life began to return remarkably quickly. Microscopic organisms, possibly bacteria or algae, colonized the crater within years or possibly even months of the impact. These hardy pioneers, living in what must have been extraordinarily harsh conditions, represent the very beginning of recovery. The cores also reveal details about how the crater formed. The peak ring, that circular mountain chain created in the aftermath of the impact, formed within minutes as rock rebounded from the shock of the collision. Granite from miles below the surface was lifted up, fractured, and rearranged. Studying this process helps scientists understand the physics of large impacts, information that's relevant not just for Earth, but for understanding craters on the Moon, Mars, and other bodies in our solar system. Modern climate modeling has also advanced our understanding of impact winter. Computer simulations can now model the injection of dust and aerosols into the atmosphere, their spread around the globe, and their effects on temperature and sunlight. These models have become increasingly sophisticated, incorporating more detailed physics and chemistry, providing better estimates of how severe and how long-lasting the darkness and cold would have been. Recent work has focused on the role of soot in the impact winter. As mentioned earlier, the global wildfires triggered by the impact would have produced vast amounts of soot, tiny particles of black carbon. New studies suggest that this soot may have been even more important than rock dust in blocking sunlight. Soot particles are extremely effective at absorbing solar radiation and can stay in the upper atmosphere for years. Models incorporating soot predict even more severe impact winter conditions than earlier models based primarily on rock dust. The debate over the Deccan Trap's contribution continues to evolve. As dating techniques improve and more samples are analyzed, the timeline of volcanic activity becomes clearer. Recent work suggests a complex interaction between the impact and the volcanism, with the possibility that the impact triggered increased volcanic activity. Understanding this interaction is important for understanding whether Earth faced a one-time catastrophe or a series of interconnected catastrophes. One surprising recent finding is that the Chicxulub impact may have affected volcanism globally, not just at the Deccan Traps. Some researchers have found evidence for increased volcanic activity around the world following the impact, possibly triggered by the seismic waves and pressure changes caused by the collision. If true, this would mean the impact's effects were even more far-reaching than previously thought. The study of the KT extinction has also become relevant to a very different field: planetary defense. The realization that asteroid impacts can cause mass extinctions has led to efforts to identify potentially hazardous asteroids and develop technologies that might be used to deflect them. Understanding what happened 6 million years ago helps inform these efforts, showing the importance of early detection and intervention. NASA's DART mission, which successfully demonstrated the ability to change an asteroid's orbit by impacting it with a spacecraft, was partly inspired by research into the Chicxulub impact. Knowing the composition of the impactor, understanding how different types of asteroids respond to impacts, these are all crucial for planning potential planetary defense operations. The KT extinction serves as both a warning and a teacher, showing what can happen but also providing data for preventing future catastrophes. One fascinating area of ongoing research involves looking for other impact craters of similar age to Chicxulub. Some scientists have proposed that the Chicxulub impact might have been part of a shower of objects hitting Earth around the same time, possibly resulting from the breakup of a larger body in the inner solar system. While no other crater of comparable size and matching age has been definitively identified, the search continues. The precision of dating techniques continues to improve, allowing researchers to better constrain the timing of the extinction and the various events surrounding it. Was the extinction truly instantaneous on geological timescales, or did it play out over thousands of years? Did all groups go extinct at exactly the same time, or were there differences in timing between marine and terrestrial extinctions, between different geographic regions? These questions require extremely precise dates, pushing the limits of current geochronology. New fossil discoveries continue to refine our understanding of which species went extinct and which survived. Paleontologists working in rock sequences spanning the KT boundary are documenting the precise pattern of extinctions with increasing detail. Each new locality studied adds data points, helping build a more complete picture of the extinction's geographic and ecological patterns. The KT extinction also serves as a case study for understanding modern biodiversity loss. While human-caused extinctions are different in kind from an asteroid impact, studying how ecosystems responded to past catastrophes provides insights into resilience, recovery, and the factors that make some species more vulnerable than others. The timescales are vastly different, but some of the principles are similar. Climate scientists studying modern climate change also look to the KT extinction and its aftermath. The rapid injection of carbon dioxide and sulfur dioxide into the atmosphere, while different in source from current industrial emissions, provides a natural experiment in how Earth's climate system responds to sudden perturbations. The geological record of temperature changes, ocean acidification, and ecosystem responses provides data that helps validate and improve climate models. As we learn more, the story becomes richer and more complex. The simple narrative of asteroid strikes, dinosaurs die, has been replaced by a nuanced understanding of multiple interacting factors playing out over decades, centuries, and millennia. Yet the essential story remains. 66 million years ago, Earth experienced one of the most catastrophic events in the history of life. An event that ended one age and began another. An event whose effects still shape the living world today. And so we come to the end of our journey through deep time, back to the present, having witnessed the end of the age of giants and the beginning of the world we know today. The story of the dinosaur extinction is more than just a story about the past. It's a story about the fragility and resilience of life, about catastrophe and recovery, about endings and beginnings. In the darkness of your room right now, safe and comfortable, it's hard to imagine a day when the sky filled with falling fire, when darkness descended for years, when the great beasts that had ruled Earth for over 160 million years vanished in what was, geologically speaking, a single moment. But it happened. The evidence is written in rocks around the world, preserved in layers of clay enriched with iridium, visible in fossil assemblages that show a world full of dinosaurs suddenly replaced by a world without them. The creatures that lived through those terrible days and years knew nothing of asteroids or extinction. They simply tried to survive, day by day, in conditions that were often impossible. Most failed. Entire lineages, whole families of organisms that had existed for millions of years, came to an end. But some made it through. Small animals hiding in burrows, birds that could survive on seeds, fish in deep oceans. And it's from these survivors that all modern animals descend, including us. We exist because 66 million years ago, some small, furry creatures found ways to survive when the giants fell. Our entire lineage, everything that makes us human, traces back through ancestors that lived through that catastrophe. In a very real sense, we are children of the extinction, products of the world that emerged from the darkness. The story also reminds us of our place in the universe. We live on a small planet in a vast cosmos, and that cosmos is not always benign. Rocks orbit the sun, and sometimes those orbits intersect with Earth's. It happened 6 million years ago. It could happen again. But unlike the dinosaurs, we have the capacity to see these threats coming, to understand them, and potentially to do something about them. The scientific quest to understand what killed the dinosaurs has been one of the great detective stories in the history of science. From the discovery of the iridium layer to the identification of the Chicxulub crater, from the debates over alternative theories to the modern consensus, it's a story of human curiosity, persistence, and ingenuity. Scientists from many disciplines, working with tools ranging from hammers to mass spectrometers to supercomputers, have pieced together what happened in remarkable detail, and yet mysteries remain. The exact sequence of events, the relative importance of different killing mechanisms, the details of survival and recovery, all continue to be refined as new evidence emerges and new techniques become available. Science is not finished with the KT extinction. Each year brings new papers, new insights, new debates. The story continues to evolve, becoming richer and more detailed with each discovery. As you drift off to sleep tonight, perhaps you'll dream of those ancient landscapes, of herds of hadrosaurs moving across plains under the light of a sun that had shone reliably for millions of years, unaware that their time was nearly over. Perhaps you'll imagine the moment of impact, the flash of light brighter than the sun, the sky turning to fire. Perhaps you'll envision the survivors, small and frightened, emerging from burrows to find a changed world. Or perhaps you'll simply rest, comforted by the knowledge that life persists, that even after the most catastrophic events, given time, life finds a way forward. The world we inhabit today, with all its beauty and diversity, was born from catastrophe. It's a world of second chances, of new beginnings rising from the ruins of what came before. Before you fully drift off, if you found peace in this journey through time, I invite you once more to like this video, to subscribe to our channel, or to share your thoughts in the comments below. Your support helps this little corner of calm reach other sleepy minds searching for gentle knowledge in the quiet hours. It's a small thing that makes a real difference in keeping these journeys possible. But there's no rush. For now, let your breathing slow even more. Feel the weight of your eyelids. Let your muscles release any remaining tension. You've traveled 6 million years tonight, witnessed catastrophe and recovery, held extinction and renewal in your mind. Now you can let it all go. Let the thoughts drift away like clouds. Let yourself sink into the soft comfort of sleep. The dinosaurs had their time. They ruled this planet for over 160 million years, far longer than humans have existed. They were magnificent, diverse, successful. And then, in a moment of cosmic accident, their time ended. But the story didn't end. Life continued, changed, diversified, evolved into new forms. The world moved on, and from that continuation came birds, mammals, flowers, forests, and eventually us, telling their story on quiet nights to help other minds find rest. Sleep well. Dream of ancient Earth if you wish, or simply rest in the peaceful darkness behind your closed eyes. Tomorrow is another day, another opportunity to explore, to learn, to wonder. But tonight, you can simply rest, safe in the knowledge that the stories of the past have been preserved, waiting patiently in the rocks for curious minds to discover them and share them with others seeking peace and understanding in the gentle hours of the night. Good night.